Hello, this is Zulongye at Computer Engineering major, and now I will demonstrate the solution of homework 11 of Ece6303, question 2. In this question, we know that if R tau is the autocorrelation function of real and y-sense stationary xt, then it is even. And have R tau is less than or equal to R0. And its Fourier transform is non-negative. Then the second one, S omega. If it is the power spectrum of y-sense stationary xt, then it is non-negative. Then we can see the following three questions. First one, question A. We have Fv equals to e to minus absolute v. We can find that e to minus absolute tau, it is even. And it is less than or equal to e to minus 0. We also have these functions Fourier transform to a squared plus omega squared. It is non-negative. Then it could represent the autocorrelation function. Can represent correlation function. And we have e to minus absolute value of omega. It is always larger than or equal to 0. Therefore, it can represent the power spectrum. The question B, we have the function Fv equals to sine v squared over v squared. We know that sine tau squared over tau squared, it is even. And sine tau squared over tau squared is less than or equal to limit tau is approaching to 0. Sine tau squared, this limit value is approaching to 1. It equals to sine 1 squared over 1 squared. We also have the sine tau squared over tau squared. This Fourier transform, it is like this: omega minus 2 to 1. And we know that this is non-negative. Therefore, we know it can represent autocorrelation function. And we also have sine omega squared over omega squared. It is always larger than or equal to 0. So it can represent the power spectrum. Question C, we have Fv equals to 1 when the absolute value is less than or equal to A, and 0 when this value is larger than A. We know that f tau's Fourier transform A equals to 2 sine A omega over omega. It is not non-negative. Therefore, it cannot represent the autocorrelation function. We also have f omega. It is always larger than or equal to 0. Therefore, it can represent the power spectrum. That's all. Thank you.